So one of our last rules that we're going to be looking at for derivatives is going to be something called the chain rule. And the chain rule is going to be a rule that we can use for composite functions. Right? So it's basically going to be whenever we have f at g at x. Right? And some examples of when we would use the chain. Let's say for some reason we had a sign of 3x, not just x. Or something like maybe the third root of 5x squared plus 2x. All right, so when we start having these functions within functions, that's when we want to go through and use this chain rule. Another example might be something like e to the x squared plus 2x plus pi. All right, so if it's not just an x, if there's anything else, we have to use this chain rule. And the chain rule basically says that what we can do is we can take the derivative of the outer function, or the bigger function, keep the inner function the same, but then we're going to multiply by the derivative of the inner function. All right, so we have this f prime inside, we have g of x times g prime of x. And this is a really tough this is really tough for students, because sometimes students confuse the chain rule with the product rule. It's like, okay, well, how do I know I'm dealing with a chain and not a product? And so you have to look really close at the function, and you have to determine whether it's being composed or if it's just two functions being multiplied by one another. Right? So we are going to start off with some really easy examples of this. All right, and just keep this one in your back pocket, because this is one that we're going to be using a lot throughout the rest of the semester, like the product rule, like the quotient rule, like all the other rules for derivatives. All right, so this is one of the most important things we're going to get out of the course, is that we're going to be able to take a derivative of any function. Just a really basic couple examples to start with as to how to implement the chain rule. So we want to take the derivative of 6e to the 4x. And notice that we have a 4x, not just an x. If it was just 6e to the x, it would just be 6e to the x. So here's how we're going to take the derivative. The 6 is a constant, so we don't care about it. So it's just going to drop down. So f prime of x is going to be 6. Now, we have a bigger function. The derivative of e to the anything x is going to be e to the anything x. So this is your f prime g of x, but then we still have to multiply it by g prime of x. And in this case, the composed function g is 4x. Right? So we have to be really careful that we pick out the bigger function, which is e, the smaller function, which is 4x. So to finish this, we're going to take the derivative of 4x, which is just going to be 4. Right? So that's our g prime in our formula. And then finally, we could just multiply that 6 and that 4 together. So our derivative is 24e to the 4x. Right, so hopefully that makes sense. Again, if it didn't make sense, go back and watch it a few times. But you do have to keep the bigger function, just take the derivative of that, keep the inner function the same, and then multiply by the derivative of that inner function. Another basic example is going to be this polynomial, x squared plus 8x plus 7 to the 6th power. So you certainly wouldn't want to FOIL this out 6 times. Okay, that would make it really difficult to do the polynomial multiplication. So here's what we're going to do. Let's take a look at the bigger function. And the bigger function in this case is going to be the 6th power. So when we find the derivative, that's going to be 6. We keep the inner function the same, x squared plus 8x plus 7. And remember, with our general power rule, we subtract 1. All right, so like for instance, if this was just x to the 6th, we know the derivative is 6x to the 5th of that. So the x just stays as it is, all right? But we still have to multiply by the derivative of the inner function. And our inner function is this x squared plus 8x plus 7. And so the derivative of that inner function is just going to be 2x plus 8. And that's what we're going to multiply to get that G prime. Right. Now, another way to write this is we can move the 2x plus 8 in front, and then we can also distribute the 6 into the 2x plus 8, not into the 5th power, because the 6 is not raised to the 5th power. So another way to write this would be 12x plus 48 times x squared plus 8x plus 7 to the 5th. Yet another way to write this, if you factored out the 12, could be 12 quantity x plus 4 quantity x squared plus 8x plus 7 to the 5th. All right. I'm not sure which way my math lab would prefer, but I don't think it would have many problems with any of these. All right. So my math lab is pretty forgiving with the factoring, etc. It's not forgiving with simplification of numerator denominator, but usually with factoring, it has a multitude of permutations that it'll take from you. All right. So another example. So let me move this back. I'm not sure what happened there. So it doesn't matter that much. So let's go ahead and find the derivative of this square root of 3x plus 2. All right. So now this is another one that's sneaky initially. All right, but we can actually very easily find the derivative of this using our chain rule. We're going to use some algebra, and we're going to rewrite this as 3x plus 2. And remember, square roots can be written as 1/2 powers. We have an inner function, which is g, and then we have our bigger function, which is the 1/2 power. So actually, it turns into a problem very much like the one that we just had. So dy dx is going to be equal to 1/2 quantity 3x plus 2 to the minus 1/2 power, because we subtract 1 from that. And then we're going to multiply by the derivative of that inner function. All right, so if g is equal to 3x plus 2, that means that g prime is just going to be 3. Right? So we're just going to multiply by the derivative of the inner function, which is 3. Another way to write this, if you chose to, would be 3, 2, and notice that we have a negative exponent, so we're going to swing it down to the denominator, 3x plus 2 to the 1/2, or a final way to write it, which is usually the back of the book answer, is 2 roots of 3x plus 2 in the denominator. So hopefully these are some good examples for you of being able to how to work with the basic chain rule for derivatives. Now we are going to look at several more, and they are going to get a little more complicated as we go on. So before you move on to the next video, make sure you understand the chain rule and how to find the derivatives of these more simplistic examples before moving on to the more advanced examples.